talk by Éva Tardos. Peter Biro asked me to be the chair today, and I was saying yes happily. And up until yesterday, this time I was not frustrated at all. But then Bettina set the bar high. So I started to think what to do, and immediately I thought that I would borrow the hat from Alex. But then, okay, I realized that we are both mathematicians, so we can just close normally. I thought I do the cheap solution, so I will talk about myself. I mean, my encounters with Éva, right? And indeed, the first time I met her was at Cornell University. So legends were rumored that Éva Tardos is coming back home with a Parkinson Prize, and she's giving a seminar. I participated in that on multi-commodity flows. I mean, so she told me during the course that whoever will be the best in the course, she will invite the person for pancake. Do you remember, Éva? I do, because I really like the course, but I thought, but the experience that I'm just nobody there. I mean, it was really difficult for me to solve even a fraction of the problems that she offered. But then when she offered me this pancake thing, I was stupid. I said no. I mean, I was not smart enough for that. Anyway, and then when I moved to Amsterdam, everyone knew her there, and I met her on a conference. At some point, she was an invited speaker. People started to ask her about her daughters. How is it going to do high-level mathematics and having two daughters and stuff like that. And when I finished my PhD, I submitted my paper to Math for a while, and guess who was the area editor there? And now I'm just realizing that from next semester on, I'm teaching algorithm game theory. And this really doesn't have to do anything with Éva. I just realized that game theory is nice, algorithms are nice. I put together the two things, and I just realized that Éva is doing the same thing on a much higher level. Anyway, during COVID, I realized that if you would like to make your lecture interesting, then you have to do it interactively, right? So I thought that this introduction should be interactive, kind of. This is what I will do now. I tell you 3 statements. One, actually, at least one is true, and you will vote. It's kind of in the idea of this conference, right? So it's quite surprising that in Éva's family, they have 3 Gödel prizes. And also, it's kind of unusual that Éva has 2 children who are semi-professional soccer players. Third statement is that I was really shocked to learn is that Éva can ride a unicycle. Okay. Vote. 3 Gödel prizes in the family. Okay. 2 semi-professional soccer players. Okay, 25%. And unicycle, 30%. Okay, so we will hear about stability, learning, and strategy games from a soccer mom.
Thank you so much, and thank you for staying for late talks. And I guess I want to add my thanks to the organizers, especially Peter, wherever he went. Peter, it's an amazing conference, and I want to thank you for all of the name of the organizers. Of these 3 statements, I guess he phrased it, none of them are true. I do agree to be a soccer mom, but semi-professional, they played for universities. 1 Division 1, 1 Division 3, that doesn't count. And Division 1 was pretty, which is a good school, but not the top soccer, so not quite true. Okay, I do want to tell you about stability and learning in games. In particular, what I'm really interested in is what happens if in a social interact in a game theory or incentive interaction, people are using some sort of machine learning to figure out what to do. So I guess I came to starting to think about game theory is this catchy phrase that Christos Papadimitriou termed as price of anarchy. And what he, and I know this is not anarchy, but that's his name. What he's calling price of anarchy is, if you look at or what he did call it at the time, if you compare the Nash equilibrium to a centrally designed optimal or some objective function, or maybe social welfare or something, how much are you losing because the players, don't coordinate properly, or they miscoordinate because of incentives. But what I'm interested in nowadays is many interactions are not one-shot things. So this is sort of a big change from what you heard Tuesday night about the incentive auction. The incentive auction, which was, I guess, to sell spectrum to people who want to use spectrum, was something that happened to people in pretty reasonable to view once in a lifetime. They prepared, they worked on it. It was in works for happening for years before it actually happened. The design was known, there were practice runs, and then they ran it once and you got spectrum. And if you didn't get spectrum, that was bad news because you probably should go out of business now. In contrast, I'm interested, and that's, there are incentives there. In contrast, I'm interested in interactions where you participate over and over again, where every one of the interactions is pretty minimal, cost is nothing, the value is kind of nothing, but overall, it really matters. And I guess the prime application that's sort of easiest to convince you is advertisement auction on the internet. So what's special about selling advertisement on the internet, that most ads are fraction of cents, like really cheap. Some of them are very expensive and then they cost a couple of dollars. But this is a multi-million-dollar industry. So there is a lot of value in here, but not in individual interaction. And that makes you think that maybe you can learn while you're doing it. A little bit of price up front for learning might be okay or might be even better. And I'll try to convince you that it's better. So there are a couple applications that I particularly worked on in this regard, and I'm going to actually maybe come closer to my favorite application all the time is packet routing or something routing, where I guess the simplest model here is that this is a congestion game and the cost depends on how many other people are using the same pass. And I guess I came to starting to do this area we call algorithmic game theory about 20-some years ago with the following theorem that says that you compare the cost of Nash equilibrium to cost of a centrally designed optimum. And what we proved, and this is with Tim Ravgarden, who by now is very famous on his own right, was at Stanford and now at Columbia, that if you design your network to tolerate double the traffic rate than what you're planning to have, I guess that side over there. So the traffic rate is how much traffic flows between coordination. If you have a traffic rate and you centrally design it for that, or tell everyone exactly which way to drive, compared to letting everyone do just optimal routing for themselves, that is selfishly find the Nash equilibrium, then turns out you're better off with the Nash equilibrium compared to what it would have been with double the traffic rate. So the way price of energy was defined actually is not quite this, because I would call this a cheat comparison, because I compared double the traffic rate to the Nash equilibrium. But I actually like this kind of thing, and we'll talk about this kind of things. What it's telling you is that you get a choice between centrally routing traffic versus increasing the capacity. Which one is better? And the answer is increasing capacity is better. Yeah, so it tells you if you choose between something that's logistically complicated versus cost some money, at least on the internet traffic where increasing capacity is not as expensive or not as difficult as increasing routing pass capacity, you're better off increasing capacity. There are lots of price of energy results that have showed up in the 20 somewhat years. I guess this first slide shows one sort of in the sharing, cost sharing, traffic sharing kind of area. Another area that's very prevalent for this, which I kind of started with, is advertisement auctions or auctions of any form. There's also beautiful results of same sort, of first price, second price, individual item auctions, how bad they are compared to a centrally designed or mechanism that's designed more central. I'm not going to much talk about this literature, except starting to criticize it on day number 1. They all, at least the early papers here, assumed that the players somehow magically find the Nash equilibrium. So as much as Nash equilibrium is super common in the econ literature, I also know that every self-respecting economist knows how to criticize it. But just in case you need a little refresher, there's some trouble with the Nash equilibrium. And I guess there are a couple of troubles depending on which aspect you're coming from. Some games have multiple Nash equilibria. Auction games have this problem, routing doesn't, but auction games do. You can ask, if they magically all of you somehow knew to find an equilibrium, which one was it? How did you figure out which one it was? But maybe more disturbingly is the red line here, the amount of information needed. You need to know who else is playing and what the hell are they doing, which is generally very difficult. And because I'm actually trained as a computer scientist, or more precisely, I'm not a computer scientist, by the way, was trained as a mathematician, which we'll show in a sec. I should say that there is technically a computational difficulty. Computationally, it's hard to find the Nash equilibrium in many games. And I guess in that case, it's not clear how all these people found it. So what I'm going to focus on is a different aspect. I'm going to think of it as a repeated game. And rather than defining the even more complicated repeated game equilibrium, I want to make a very simple assumption and maybe want to convince you that that's not actually a bad assumption of what's happening out there in the real life. Is that we repeat these games, and again, think of games like advertisement auction when the individual cost is not so high. And people somehow play, initially maybe a bit clueless, but play over and over and over again. And as time goes on, maybe they figure out what's good for them. They're selfishly optimizing. They're not forming beliefs. They're not forming knowledge about who are the other players. They're just observing what happens. They say, if I bid only $1 all the time, then I don't mean a damn thing. That's not good. Let's bid a little bit higher. If I bid so much, my money is running out. I guess, maybe I should bid lower or something. They selfishly, simplistically optimizing. So I'm going to assume, which is the red line here, red part here, that players are trying to take whatever is happening in the game and learning using some sort of learning algorithm. And I'll come maybe clean of what exactly I mean by a learning algorithm, but for now think of, my whole field, computer science, is not taken by how to design these algorithms. So one of those, learning algorithm. And I want to ask, what exactly happens if everyone does this? So the main question is, what can I say about the learning algorithm? I also want to say, and that's what I maybe started with, I have to be a bit more clear on what the hell do I mean by learning, or maybe think about what I mean by learning. So maybe you all know this, but learning in repeated games have a long history in econ. And I like saying the sentence that starting before I was born, which, I guess I'm old enough. This is definitely before I was born. And I guess one of the early learning algorithm was something called fictitious play, where people just somehow simplistically react to the distribution of other play sections from the past. And I guess was signed by Brown and Robinson. Julia Robinson in 51 proved that in 2-person zero-sum games, this actually converges to Nash equilibrium, which I think is a beautiful statement. But the way they view this is learning was a way to find the equilibrium, or maybe another way to use it as a pre-play. kind of more like the incentive action. You practice in this algorithm, and hopefully practice will lead you to the Nash equilibrium. I would say that this turned out to be not so fruitful. So I guess mostly learning algorithms of any kind don't find the Nash equilibrium. I guess there are these two very simple theorems from early on. That person zero sum games it works, and or generic payoff 2 by 2 games it works. There are some other things that it works, but most games it's not. And I guess, again, as a computer scientist, these are algorithms. We know it's computationally hard to find it, so the algorithm won't find it. I guess since we're celebrating Vince's birthday, I feel obliged to point out that Vince was one of the early contributors in the econ community. I guess Brown and Robinson were more mathematicians or statisticians. So Vince was an early contributor in this area, thinking about some of his papers. He's still thinking about what are the class of games where this actually finds the Nash. And I guess he pointed me in discussion yesterday to a very nice note by John Levin that sort of summarizes part of the issues here of what does or doesn't find the Nash equilibrium that's more recent. I want to do a change of focus here, and I want to convince you that that change of focus is interesting, and my whole talk will be about the change of focus. I don't want to ask whether it finds the Nash. I don't care. It might not find the Nash. I don't care what it does. I want to know what happens to the game. How good are people feeling, but what happened to them, or what happened to society when everyone did this, whether or not it found the Nash. Okay, that's my plan. So I guess the plan is maybe when they start, they don't know what they're doing, but as time goes on, hopefully they get better. And I want to make simple assumptions. And I guess this is all somewhat applicable, or hopefully applicable, again, in settings where the individual actions or the individual actions are very small consequences. They don't matter much, but overall it matters. And this is true both on packet routing. The way the internet is set up, if one packet doesn't get to the destination, they just resend it. It's very well designed. Nothing happens. Like, you don't even notice. You watch the movie, you don't notice that one of your packets got lost. So not a big problem with one mistake. The same on ad options. If one ad is not shown, no problem at all. But overall, both the internet and ad options in particular are multi-billion-dollar industries. So overall, it matters. So what would it mean for learning of any form? And again, I haven't told you what learning is, which is coming now. What would it mean for learning to find the Nash equilibrium? It would mean something like this, and I didn't quite reach it, but maybe converge to it. You do something in the beginning, and then you find yourself in what's a Nash equilibrium, and learners, because this is, Nash equilibrium, they don't want to deviate anymore. So then they repeatedly play that option. So what's the property of that option? If it's a Nash equilibrium, this is the property that we want. Maybe this is a game with utilities like auctions. Your utility that you have in this auction profile A is better, or at least as good as any other action you could have taken. That's what it means to be Nash. And what I want to do is actually keep this, which I'm going to call the no regret condition, but get rid of the stability assumption, get rid of the assumption that they converge. So assume this without assuming stability. Why am I doing this? Because if you look at real life, and for example, ad auction is where I have data. I have ad data from Bing auction on Microsoft. It's just not stable. Behavior is not stable. This is what it looks like. These are very well, these are bidders who obviously use some of those bidding tools. I don't know if they have their own company bidding tool or actually hired someone to bid for them, but they used only bidders for this exercise who change their bids very frequently, and they have insanely high budgets. So they're trying to just optimize their bid. That's what they're playing, and this is what it looks like. And they have lots of plots like this. They were changing their bids all the time. So they didn't stabilize. So what I want to do is actually assume the following behavioral assumption, which I guess in the computer science literature is known as no regret condition. And I guess it's taken off of the no regret I had there that's required for Nash equilibrium. Here is the condition. You can change your grid all the time. You change your behavior all the time. Obviously, that's what you do when you learn and experiment. But if there's a single consistently good solution, please notice. So here is the condition. The utility you get over time should be at least as good as any fixed action with hindsight. Going back to the routing thing, if there, and I guess Germany is maybe the right country to use here because there's so many paths going north to south or south to north or whatever direction, is you can drive on different routes every day. You can know that, that route is better when it's raining and this one is better when it's sunny or whatever. You might be very, very smart, but there is a single route that's consistently better than what you're doing. You didn't learn. There was a really good solution and you didn't wake up to this. And it was very simple. It was a single at the time. So that's going to be my learning standard. And that's the notation for it. And when I said that better than a single thing with hindsight, I do give you a little bit of an error because upfront you have to learn. So this went up for time t, capital T, and little of t is the computer science notation that it grows slower than t grows, like, for example, root t or something like that. So as time goes on, you're roughly speaking doing as well as or much better than a single thing with hindsight. This is a beatable benchmark. And I'll show you data in a second in the adduction. People beat it. They do better than this because they can figure out that they can vary their behavior with something that works well in life. But if they don't even match this, I'm going to claim that, well, they didn't learn. So actually, if you repeat the same game over and over again, literally the same game, and everyone behaves like this, then the game converges to something that's known as a form of equilibrium, a form of correlated equilibrium, technically called coarse correlated equilibrium, but a version of correlated equilibrium. So it does match something that the econ community uses as a name, correlated equilibrium. I have a slide here trying to convince you that you should like this. I'm quite aware, and due to lack of time, maybe I hid the slide of what are the negatives, but I can happy to take criticism. You can raise your hand and criticize it if you want. So that was the condition again. The utility that you have from playing should be not much worse, with a little bit of error, than any single strategy with hindsight. So here are a couple of positives. No need for prior. You don't have to know who's playing against you, who's there. You just learn, run a learning algorithm, and you check this. Even maybe better, if the environment is changing, learning algorithms can adapt to this. Whereas the Nash equilibrium notion, you have to know to adapt your beliefs. To me, it feels like a very reasonable behavior assumption. Like if there was a single good strategy with hindsight, how come you didn't notice it? Please notice it. So it's not a bad assumption. There are many, many simple algorithms, and what they really do, and roughly everything of this form actually does it, is you randomize, you look at what historically was good and bad, and if something is bad, you decrease the probability something is good, you increase the probability. That's all. Very simple. Virtually anything you do in this framework will actually do it. So it's almost like fictitious play, except it's not deterministic. If something is historically the same, you should randomize between them. But why I like it, and this is where it's coming out that I'm actually trained as a mathematician, because it's a nice inequality. It's very usable in theory. It's an assumption. If I make it, I can do nice theory off of this assumption. And for example, an early work in this area, the Robinson zero-sum game is repeated under this assumption. I don't have to, Robinson assumed that they're doing fictitious play, named what they're doing. But I guess this theorem here by Freund and Shapira says, that's not what they do. It doesn't matter what they do. If they satisfy this condition, then they will converge to Nash equilibrium, which I think is sort of nice to know. There are a bunch of behavior assumptions or experiments suggesting that, you know, this might actually work. I listed here a couple of papers. I guess the Arrows paper up there is a lab experiment. I guess the second one, Friedenberg and company paper, is also a lab experiment. Actually, all of them except for my own lab experiments. To be honest, the message on different papers are a bit different in what they say. Like Friedenberg paper, for example, says that, you know, they don't satisfy this condition because people tend to be recency biased. Does it mean recency bias? You don't actually edit all the past. You favor the recent past, which, you know, that's not a bad idea. And one can do this algorithmically also. So they do a variant of this. The Noam Nissan paper says that, you know, some people are so frustrated because of some reason I gave them a stupid, really boring task that they behave badly. But the people who could make real money satisfy the condition. So there are variations of what they actually say. Our result is from big data. Big is the Microsoft adoption. And this plot is maybe useful to see here. We have about something like 30% of the bidders who are doing better, but more than zero regret, less than zero regret. That is, they're doing better than single thing is hindsight. So these people here, this big bar here, are actually beating the benchmark. They know something that I didn't know in the data. And then the other guys here, you know, 10, 20%, a few people are doing worse than that. But most of them seem to satisfy the condition. So it's not a crazy assumption to make. The second thing I liked about the assumption, and this is maybe where my research is heading. So remember, Koutsopias and Papadimitriou defined price of energy, and that was the definition. You take any Nash equilibrium, the utilities that people get, so averaging every month or summing up every month's welfare, compared to a centrally designed optimum, how much did you lose? And then there is this beautiful sequence of papers, starting with Avram Blum and some students, and beautifully summarized by Tim Ravgarden, that our proofs here are so damn simplistic that they automatically extend to repeated games if everyone does not regret. Again, don't have to assume what they do as long as they satisfy the condition. And I guess, you know, this sort of gave our community, or certainly me personally, the message that I don't have to worry whether I can predict what people do. In learning, there's a lot of randomness, and depends where it converges on what exactly happens with the randomness. But it's possible sometimes to predict properties of the outcomes without predicting what exactly will happen. And this time it predicts that, you know, social welfare is pretty high. People are overall average are pretty happy. Individually, I don't really know, and I don't know if the outcome will be that Vince is doing well and Peter is doing badly, or the other way around. But overall, we're actually doing pretty well. So I predicted that, or these theorems predict a property of the outcome without predicting the outcome, which I really like as a sort of something that one can do in this case when outcome is a little unpredictable. To be honest, part of this extension theorem is might be telling you that our proofs for the price of energy are so simplistic that it's easy to extend. And I won't actually give you a full proof, but maybe give you one hint of how this is going. The bad news is, or that's the simplicity, that the only things the proof use, that if this maybe A as an action vector, whatever that is a Nash equilibrium, then and A star is what you should have done in the socially designed optimum. No one desires to switch to this. That A star for everyone individually switching is worse than people switching. And that's the only inequality that gets used in the proof somehow, other than properties of the game. And this is nice because that inequality, one for one replaced with the no regret condition. Okay, with a bit of error. So any proof that only used that inequality naturally extend, and this was really what's happening here. We even extended it to cases where the population is changing, and in this case, the population is changing, but should do a recency bias version. So, you know, between this, and these are all theorems roughly like a bit less than 10 years ago, the community, me definitely included, all concluded that no regret is beautiful. It's a nice behavioral assumption. It's easy to satisfy. People tend to satisfy it, and we can prove all kinds of things with it. So my next agenda, and what I want to tell you in a little bit of how much time I have, is that there are things wrong with this assumption, and maybe one can do more sophisticated things, or I hope one can. And here is what I'm going to ask. A critical assumption in these proofs is that you literally repeat the exact same game, that the game doesn't evolve as you change things. So what do I mean? You play a copy of the literal same game, and the only thing that you carry between iterations is your memory. Yeah, you remember how it went, and the other guys remember how it went. But that's all that happened. And in any of the application I mentioned, you can reasonably tell me that, oh, that's crazy. Of course the game evolves. So just to be on the same page, let's go back to this morning of traffic routing. It depends on your time scale, of course. A morning rush hour, sure. Yeah, no matter how bad Monday morning was, those guys went home by Tuesday morning. Kind of, guaranteed. But if you do millisecond by millisecond packet routing on the internet, obviously not true. In fact, it's not true on cars if you do it even like, half an hour by half an hour. Like it depends on your time scale, on the traffic routing example. So the actual result I'm going to tell you a little bit about is actually a very, very simplified version of packet routing. It's a joint work with my ex-student Jason Gayatonda, who is now a postdoc and will be on the job market next year. And he's an amazing guy if you're interested. It's going to be a very simple model of packet routing, trying to actually model the internet. Where what happens is that if a packet doesn't go through and you drop it, the system resends it. That's a carryover effect. If a lot of your packets get dropped, you keep needing to resend. There are more and more stuff to resend. So that's a carryover effect. But maybe a killer, and maybe that's a nicer proof, a killer application, that non-killer application is budget deductions. So we have heard during the couple of days so far about budget deductions. So people have a budget and they can't spend more than the budget. What's interesting here is I do repeat deduction, and the budget is not for one run, budget is for the months. And if you think about how internet auctions works, I don't know if how many of you try to actually try out advertising on anything like Google. How many of you try, who tried to put up ads on Google just as an experiment? Oh, okay, even better. I think we put in. So the very first question they ask you, what's your budget for the month? After that, they ask you what you want the ad for, what you want to do. But first they want to know, what's your budget for the month? There is a budget for the month. So in that case, it's not the individual auctions that budgeted. You can spend $1, 10 cents, 1 cent, whatever. But over the months, you have a budget, and that's a carryover effect. If you win a lot in the beginning of the month, then you run out of money in the end of the month. In fact, there are funny experimental things that my friends at Google and Facebook are telling me, Meta, whatever the company is called, is telling me about what's the difference between the ad prices on the 31st of a month and the 1st of the next month. There is a significant difference because budgets. Because 1st of the month is the next month's budget. It's a whole different game out there. So budgets are very important, and there's budget deductions. Same problem. Carryover effect is how much money is in your pocket. So the things I've been working on the last 4 or 5 years, maybe more, is this kind of auctions, examples of auctions, but I want to do the same sort of results. I want to say, if everyone's learning is the right kind of learning, what can we say about the outcome? Hopefully something reasonable. And if there is dependence between the rounds. And the kind of questions I want to ask is, first of all, is no regret good enough in the presence of this dependence? In the queuing version, I will ask the question I actually like better is, how much capacity do you need to actually be successful despite lacking coordination? So everyone just learning on them. And in the auction format, where I will tell you a little bit of, very little about, is about social welfare again. Just to give you the punchline, so you sort of think about what the plan of the next some number of minutes are. I want to do two things. In the queuing application, I want to tell you what the application is. I actually formally define a problem, which I so far didn't do. Define the queuing application and give you maybe not, definitely not the full proof, but a little bit of a proof to give you a sense of why is this no regret condition good? How does one use the no regret condition? What does it mean that I want to use the no regret condition? And I guess that's very nicely doable in the queuing application, and I'll try to give you a hint of what's happening in the queuing application. And then what I want to do is basically try to tell you what way is no regret not good enough. And to be honest, that's a better open question than any answer I currently have for this. I have hints and suggestions of what's wrong with no regret, and I even have guesses that people's learning algorithms are better than that. Even the practical machine learning algorithms are better than just simply satisfying no regret. But I don't have anything yet to show you as a result. So here is a very simple queuing model question. There are queues, many of them in blue squares, and they're servers, and they're getting packets that they want to send to the servers. You can think of it as packet routing on the internet, though I gather there will be a more complicated system there. I'm going to make some very simple assumption. Every queue has some packets arriving at some Bernoulli rate, probability lambda I, every iteration I. Every server has an ability to serve. It's capable of serving a packet is probability mu j. Each time, every queue can only send to one server. That's literally how the internet works. The routers can only send one place. Maybe you're not surprised. Every server can only serve one packet at a time. That's how servers work. The part that I'm slightly cheating on and definitely makes an interesting learning example, but a bit oversimplified as a model, I'm going to assume that a packet that's not served is instantly dropped. And I admit how the internet works. There's a tiny, tiny buffer, and a couple of them they store, and then they start dropping. That makes my life more complicated, so I'm going to assume that there's no buffer. As soon as you can't serve something, you drop it, which means that we have to get resent. I guess I sent it in resent to the queue, but really is happening is a lack of acknowledgement goes back, but basically you have to get resent. And then the most important thing, maybe not most important, but important, that servers try to help you get through, which turns out to be really necessary, is when possible serving the oldest packet among the arrivals. Okay, so what can we say about this system? First of all, queuing theory 101. So I never took a queuing theory course, but this is really 101 lecture number 1. So this much hopefully is easy. Is if there's only one server and one queue and one server, then the rule is that if the arrival rate is strictly less than the service rate, then you're okay. And if it's not the case, then it's very not okay. You're not surprised to hear that arrival packets arrive faster than you can serve them, then obviously you're not okay. It turns out if they arrive less fast, then you're okay, and don't worry about the info. That's a sort of edge case I'm not worried about. Okay, so that's sort of the basic queuing theory 101. So what you need is that lambda is less than mu, then you're okay, otherwise you're not. Now, what happens if there are multiple of them as my baseline measurement? What happens if there are multiple of them, but I'm willing to coordinate? Turns out a very similar condition will work. So for notational simplicity, because I'm coordinating, I might as well assume that everything comes sorted. So, you know, the lambdas come sorted and the mu's come sorted. And then I can write the conditions sort of a bit more simplistically, though it's still a bit hard to read. So let me try to read that for you. So it says that something happens for every k. So let's start with k equals 1. So k equals 1 says that if I take the queue that gets the most packets, there should be a server that's capable of serving that. Remember, even if he was alone, he needs it. He can only send to one place. And, you know, if there isn't a good enough server, he's in trouble. So that's a condition. Second, k equals 2. If I take 2 servers and look how many packets they get combined, the 2 of them can send to 2 queues. So hopefully there's enough capacity on 2 queues, and so on. And turns out this is a necessary and sufficient condition. If you coordinate, this is enough. And so what I'm asking is, how much more capacity do I have to give to guarantee that learners can get through? We'll see that this much is not enough. In fact, we need a factor of 2 up. So the theorem with Jason Gaetonga is that if you give it twice this capacity, then learners can get through. Turn out this is time. To slightly foreshadow what's happening in a second, so I'm going to give you a bit of a hint of how Norigat is getting used here, that this is big, and I feel bad about it, or you should feel bad about it. And we actually have an improved theorem that if they were not as simplistic, but somehow as Norigat turns out to be, but more forward-looking or patient, then this little bit of less blow-up in capacity is enough, and I'll come back to that in a second. So what I promised you is maybe I spend a couple of minutes on giving you a hint of why is Norigat good, which is a hint of this proof. And you can forgive me, it's my mathematical training, it's hard not to say anything about proofs. There's a very powerful mathematical theorem that we're using. Here is the theorem, and it feels very believable. If you have a process of random numbers like 5, 7, 8, 10, 2, whatever, varies up and down. It's 2 properties. I will be skipping on the first one. It should be somewhat regular. Don't worry about it now. But the most important one, if the number is big, it tends to come down. So it says if it's sufficiently large, then it has a negative drift. It tends to come down. Then these 2 mathematicians, Pimentel and Rosenthal, proved that in that case, in expectation, it stays bounded. This is very believable. It can't go very high because of the regularity. It can't jump, and it can't keep coming up because when you're high enough, it will come down. That's what the expectation says. This is what the theorem we use. We use it with the following function, which is the sum of the ages of all the packets. This is a good potential function. So tau is the age of the packet, and I add up all the ages, and that's my potential function. If this phi function stays bounded, then even one packet cannot get very old, because that will push up that function to whatever age that is, not to speak about all the other packets around it. So if phi stays bounded in expectation, then the q's have to stay bounded in expectation. What I want to give you a hint with basically 1.5 slides is how the factor of 2 and Norigat combine to actually give you the negative drift. And again, I told you, don't worry about the bounded moments that are sufficiently regular technical data. So, okay, I want to think about some of the ages. To do that, I want to focus on a particular age for the proof. So say tau is some tau, or there are a bunch of tau old packets. I'm looking at what are these old packets doing? And remember, these guys have priorities. So I'm looking at the long window and what they're doing. And I ask myself one question. Are these old packets know to use the best servers? They have priorities. So if they use the best servers, they get served. Very cool. And I don't even have to have them use the best servers all the time because of my factor of 2 blow up. If they use the best servers half of the time, I'm golden. Half of the time, because of my factor of 2, is good enough to get rid of these packets. So that's one case. What happens if they didn't use the servers? If they didn't use the servers, then wait, those servers were empty half the time, as far as they're concerned. They were using your possibly serving younger packets, but these guys had priority. So why aren't they using it? They must have regret because they should have used it. What does it mean that they don't have regret? They're getting this kind of service someplace else. So this looks like the factor of 2 looks tight for the proof, and in fact it's tight for real life. Again, the argument is either half the time you're using it, and because my factor of 2 blew up, that's good enough to get rid of you. Or you left it empty half the time, but then that empty spot, you had priority. You should have gone there. That was a really good solution for you. Why didn't you do it? I guess you must be getting this service someplace else. Fine with me. That's okay also. So that's basically the proof. And then I guess yet another technical detail is that I said this for one age group. I should do it for all age groups and add it up to get the band. I'm slightly simplifying some technical details, maybe not so slightly, but really this should give you a hint of what's no regret good for, and why is it that no regret does need this factor of 2. It's really tight. But I want to give you a little bit of a hint that something better is possible in 2 steps. I was told, and hopefully you will agree, that a theorem of the second kind down here, that in some patient version one can do better, is not taken kindly with the econ audience because I didn't define the problem. So here are 2 things I want to do for you, at least define what the meaning of the theorem is. And then instead of showing any proof there, just give you an example that should give you a hint that, oh, I see what's going on here. And hopefully you'll feel this way. So what's the actual model is this. Every queue should choose a probability distribution of how they send in packets. So you send this 50% this way and 20% that way. Everyone makes that. And then the way they evaluate it, and this is what I quote patients, is not individual success rate, but how fast is the queue building up behind you. So, ideally, you don't have no queue because nothing built up. That's lovely. Then you succeeded. But if you have a queue building up at the rate of some rate, then you're less happy, and that's your objective function. You're trying to have it not build up. That's your goal. And that's not a myopic goal, it turns out. That's a long-term goal. And that's why it's different. And then we look at the Nash equilibrium of the game. And what I'm missing is I don't have a learning that guarantees this. I only have it as a Nash equilibrium does that. But I was hoping to give you is an example that gives you and illustrates what's going on here. And I think the example is maybe more insightful than proof. So here it goes. So 2 queues and 2 servers. Arrival rates are a little bit above 50%. There's a perfectly good server, 100%, all the time succeeds. And there is a pretty shitty one, between less than 50%. So what I'm indicating is a particular strategy by these 2 queues that they deterministically always send to the better server. And not too surprisingly, in that case, roughly they get a 50% service rate. There are 2 of them, you have to choose between them, 50%. Okay, couple of things to notice here. First of all, this has no regret. 50% is better than 47%, so 50% is good. Of course, also, because I made them in arrival rate bigger than 50%, they're not going to succeed. They're not getting the package. If 51 plus 51 is 1.02, they're going to build up packet build up. So they get linear growth of packets behind them, so not good. Here is the interesting part. Of course, if you were to deviate, so one of them say decides 90% up and 10% down, you might think that this is an altruistic move. I leave the upper one 10% for the other guy. That's kind of nice. I'm suffering here is by 45%. And they have regret. But turns out this is a good selfish move. Everybody gets through. So why is that? There are a couple of reasons. First of all, the top guy won't have packets. So sometimes when the bottom guy goes up, there will be no competition there because the other guy ran out of packets. Also, it will tend to be the older one. So you get an even better service rate than 50% up there because he did this. But if I look at the way we analyze the Nash equilibrium, long-term packet growth, this is a selfishly good move. So in the Nash equilibrium, they'll do this because they both get zero packet growth. So the long-term evaluation is better. In my simplistic way, they have regret. So maybe the next couple of slides are better for an audience that have done no regret learning since we were babies. Okay, not. It became popular in the CS community in 80s, I think, late 80s, early 90s. But here is the trouble with no regret. First of all, I had a broken notation. So let me fix the notation first. I said that it didn't have these upper indices up there. I didn't have this 1 through T because in my notation, I implicitly assumed that the past doesn't matter. That was wrong. The past does matter. So in my new notation, I said, well, actually, the utility at time T doesn't only depend on T, it depends on the whole history. And the same here. And if you think about what these no-regret algorithms do, there is a phrase for this that's called explore exploit. That you try other strategies, just think it, try it once. If it works well, you try it again. But if it works badly, you back off. I remember a queuing example. When you're having the 50% success rate and you try this 47%, it works worse. You back off. The no-regret algorithms are doing the wrong thing. They don't evaluate long-term effect. They set instantaneous effect. And in notation, this is the dumb thing they do. They keep our old history as it was. Try X for a second and back off. This is not what we meant. What we meant in English was more this thing. That is, what would have happened had I done X all the time? I would be much better getting it. But the algorithms do the top thing. They don't do the bottom thing. So now I admit the bottom thing is a little too strong because how the hell did you know what X to do? So I should adjust this to adjust for upfront learning. But we need a condition like this. There are algorithms that achieve conditions like this. I have to think about this, of exactly what we can prove with those algorithms. Before I want to end in the last minute, I want to tell you that we do have some theorems on auctions, and the very same problem shows up on auctions too. And without sort of spending significant time on this, at least I want to tell you sort of the bottom line of what's going on. The budget. The long-term thing that no-regret learning is forgetting to think about is running the guy out of budget. So say Vince and I are participating in an auction, but turns out I'm really poor and Vince has a lot of money. We can do it backwards if Vince prefers it that way. If I bid very aggressively and Vince is backing off because of this, then he made a mistake. He should have run me out of money. He should have bid higher so that I run out of money. This is a long-term effect that, going back to that slide, the bottom condition will notice the top condition doesn't. And that's what no regrets doing wrongly. Concretely, we actually do have a positive theorem on first price auction, and this is actually harder to do. But second price auction, no condition of no regret start can do anything at all because it's not taking into account that we could run the other guy out of money. And I guess in conclusion, I do think that learning players achieve high social welfare. I like actually even sometimes this carryover effect. I like that no regret learning is a beautiful assumption, and I like it as a behavioral assumption. I less like it as a naming what is the algorithm, because that is kind of problematic to actually name what people will do. I like naming a property. You learn if you satisfy some property like no regret, and I can think of other properties possibly. But no regret is a bit too simplistic here because it's not thinking about assumption. And I guess the open question here is, can you do something? Is there something better? And possibly even like no regret, but think about long-term effects a bit more, which is not that hard to do. In fact, in the queuing algorithm, it might be that even with a better learning algorithm, even our 1 - 1 over E or 0.6 pound might be beatable, because the worst case is this super unstable Nash equilibrium. So that's no learning will converge to something this unstable. So hopefully we'll even do better than that. And in the budgeted auction, can we say anything about first price if the player's algorithm is smart enough to attempt to run the other guy out of budget? And I'm going to stop here, and thank you very much for your attention.
Feasibility of number. Seems to me that you might not always have the information that it takes to make sure that the condition is satisfied. So I would have been less puzzled had you said, I'm going to assume that people are trying to minimize regret, and also possibly had you created a learning process that did that.
So,
I think you talked a little bit about this in the middle, but you were going.
so there is a large, ginormous computer science literature that's creating processes like this.
Okay,
So,
to minimize regret or to ensure no regret?
ensure vanishing regret. They really care about whether that error term at the, what I said, law of t, is it root t, or is it log t, or is it, sometimes it's as bad as 2/3 to t. They all are growing less fast than t, but how slow they grow, they really care about it. They love the log t, they like root t better than they like 4/3. To be honest, if the bidding space is very high dimensional, then there's computational difficulties in achieving this. In low dimensional bidding spaces, so you set a fixed number of parameters, so a small number of parameters, then they're very elegant, very simple algorithms. And the message I was trying to say is that, especially in one-dimensional bidding spaces, almost everything does it. Like the philosophy that you should be different from fictitious play is don't make it deterministic. If two things were historically the same or roughly the same, choose them with the same probability, because that's the bad examples of fictitious play were that way. Like fictitious play does really, really badly on a coordination game because you constantly miscoordinate. Why was it? Because the experience is almost equal, and that tiny trade-off is always going the wrong direction. But if you randomize it, isn't happening. So in a one-dimensional or small-dimensional bidding space, these bands are very easy to achieve. In high-dimensional, and you don't need the information, and like you can achieve it with very low feedback. So the other thing I swept under the rug is that the error bands on that law of t depend on how much feedback I give you. So the full information feedback, you know what would have happened had you done something else, which is possible in an auction phase if you not only know that you lost, but you know how much what was the bid of the guy who won, like how high do you have to bid to win. But you can actually achieve this with a bit bigger bands on the error term, still not growing as fast as time. Even if I only give you only the feedback you observe, like only your experience, you lost. Sorry, bid was too low.
My paper with Howard, you mentioned, does show that it's uniquely optimal to randomize in these repeated coordination games. And I later discovered that there were computer science folks who had been doing the same kind of.
So there is a huge literature. They have to have there's two big machine learning conferences that have a lot of this, NeurIPS and ICML. But there's actually a somewhat smaller conference called, which is the theory of conference on learning theory. Maybe on conference on learning theory stands for COLD, who are literally doing exactly these bands. Like these theoreticians, they want to prove bands, and this is the kind of bands they want. And they're different environment, like they're different variations.
Questions?
Very interesting talk. One question I had is how excited are you about EQ learning and deep reinforcement? Like Google's had amazing success. I understand that EQ networks have discovered optimal auction design Myerson's results.
Yeah.
So it's like you put these smart robots in to do self-play and they learn the equilibrium.
I'm super excited about the whole area. And in particular, I should advertise that on August 13th and 14th, Francesca Molinari and myself are running a conference on learning and economics at Cornell. It's a 2-day conference, 6 keynote speakers. If Peter is willing to help me, I can send it or put it someplace. But the pointer for the talk would lovely to have many of you come. As best as I can tell, the econ community is an econometric society conference, and we got 460 submissions for contributing papers. So we had to reject a bunch of them because there wasn't room for that. I'm very excited. For my own research, as I admitted, mathematically trained, and I'm still a theoretician. So I would love to prove stuff about them. But I think learning the experience and having data for what happens when people do it, whether some model of behavior model is reasonable or not reasonable. I definitely would love to see what these things can do in practice. I also would love to be able to prove some guarantees under some behavioral assumptions. But yeah, it's definitely super exciting.
Other questions? Charlotte, please.
I'll ask a somewhat stupid question, which is probably up on yours. How excited are you about the ability of these algorithms to learn to collude? Thinking about marketplaces and thinking about kind of the current legal framework.
Yes.
What constitutes.
So yes, that's a very relevant point. And I guess actually the first people who started to think about what's wrong with no regret is people who wanted to collude, I guess. So they didn't call it collusion. It was play in repeated prisoner dilemma. And the only one more regret actually in prisoner dilemma is to defect. But in a repeated prisoner dilemma, that's a dumb thing to do. If I cooperate, maybe I convince my opponent to cooperate. That's the same problem we're having, that there's a long-term effect here of convincing the other guy to cooperate. So that's definitely, there's a whole literature that's trying to understand this. Very interesting, but not so successful at this moment. And understanding how to do this, how to prove anything about this, but definitely there's a potential there. And there are attempts that I know in trying to sort of redefine the legal framework of what does collusion mean here, or what should be allowed and should not be allowed. And I guess one sort of interesting thing is, if you do very simple no regret learning in auctions, multiple players learning how to bid in auctions, they will collude, actually. They will automatically learn to collude, which is a very fun, especially reinforcement learning does it. But all kinds of learning does actually generate collusive outcomes in a weird way. So this is a very exciting area. Like I need to better understand what happens. From my very theory perspective, the simplest algorithm that they generate collusive outcomes, they don't do proper no regret. They don't correct. These are partial information algorithms, and they don't correct for the partial information properly, but the outcome is better for them. They are actually colluding. The second price auction, they collude, which is a fun, interesting fact. And there's some interesting legal questions here also. How should we define collusion? Or what should be legal? Because this algorithm is colluding, people didn't talk. They just ran and not so proper nothing found.
Last question. Comments? Come on.
Yeah, I have a question. I mean, if you think of the traffic problem, yeah, and the technology we now have, I mean, the traffic planner, yeah, he sees exactly where the cars are at this moment. Isn't it the best that everybody gets a signal? Let's say there are only two roads, A and B, yeah, and everybody gets a signal. And maybe you don't know anything where people really want to go, but they don't have to follow their signal. Yeah. You are told to go to road B, another person on road A, and let's say they make mistakes, or they just switch. So on average, it will be much better than if everybody goes just like themselves and learns where the traffic jams are, because there could be like this level of reasoning. Yeah, you could say, oh, this is empty, so everybody switches to the empty street. Yeah. So anybody thinks, I mean, Google gives the information, but not signals.
I guess, remember, some of you might remember the old times when we had to buy these machines with GPS in them and traffic, like it wasn't in our phone. We had to buy a special thing for our phone. At those times, the German company that was generating a signal, I had friends in the practical OR community that were trying to do this. And what they were trying to do, and they never were public about the parameters, is give people advice which is within some small alpha percent of the best route there is possible right now, and what I don't know is what was alpha, but say 5%, I'm making it up. Within the best route that they can give you, and given that constrained optimized routing. This is unfortunately not a linear optimization problem, but a complementarity problem because of you cannot give someone something that's less than 5%, so 5% better than worse than what they could have, what the alternate best route is. That makes it a computationally hard problem, but these are practical OR people who were solving this hard problem in the German, like Germany as a country democratic. I'm not aware that anyone's Google is doing this, which I'm paying. So it would be like Google should be doing it because Google controls so much of the traffic. I know people, I know papers that people did this whenever we had these devices, and I only know it in German. But you're totally right. There should be something like it.
Level one reasoning and then half of them.
So that they do that. They do that. What they don't do is what this German company at the time was doing is a hard global optimization problem that they were aiming to solve, which I think is not happening.
It can go either way, depending on the pattern of congestion thought, that can be better to have people going randomly or choosing the best route.
But Google is randomizing, it's not giving everyone the exact same ones.
Okay, so I suggest to continue it offline. Sometimes all effective and